Okay, hi everybody, welcome back. So this is part 2 of my videos, second last part about guidance for the Product Engineering Group Project 2023 version. So in part 1, I talked about the algorithm, the conceptual side of what you want your robot to do, what you need your robot to do in order to do the easy or medium versions. Today we're going to look more at how you might structure the code. Now, things like how do you control the motor speed, how do you take readings from the time of flight sensor, those sorts of things are all handled in the workshops, weeks 6, 7, and 8. So this video is not going to cover that. It's going to cover instead sort of the overall structure of your program. How do you give you some guidance on how do you tie all of these things together in order to get the overall behavior that you need. So I'm going to talk a little bit about the overall structure of your program. Oh, wait, let me just get a laser pointer case. So the overall structure of your program, essentially where you should put all the different things. Then in part 1, I talked about finite state machines and how even the easy version kind of needs a finite state machine to allow the robot to be in multiple different states, either waiting to start cleaning, or going straight or turning corners and all of those things. So there are a lot of ways that you can implement a finite state machine in Python. There are classes available. You can get quite complex classes that allow you to build very complex state machines. I looked into that and ultimately decided that I didn't think it was the direction to send you, because I don't think we need a lot of the more advanced functionality, and it's just harder to figure out how to do it. So what I'm going to show you here is how to just do quite a simple implementation of a finite state machine, which can be an extended one if we use global variables to keep track of some other information. And it's basically just all coded yourself from scratch. And as you'll see, it's pretty simple. And then I'm also going to talk about a few approaches that you can use to timing behaviors. So checking sensors at a certain rate, updating your control loop at a certain rate, getting a value that is a function of time, like sine of something or cos of something, those sorts of things. Okay, that is, I think, all I wanted to do with, oh no, I'm sorry. There we go. Okay, so before we jump across to Mu and look at how we do this in actual code, so basically the whole program doesn't fit on my screen at once, so I'm going to have to scroll you through it, and therefore I thought it might be helpful to show you just as sort of these little blocks, the overall order. So I'm not sure to what extent which aspects of this order are like mandatory, you know, whether your program won't work if you do it in a different order, but this is very much the sort of conventional order. This is the order I use in all of my examples that I give you, and so it's the order that I suggest you stick with. So first thing right at the top is we have any import statements that we need to import libraries, modules, functionality from elsewhere. Then if you are creating any classes yourself, and as I've said elsewhere, you can do the group assignment without implementing any classes, but implementing the functionality for the getting speeds from the encoder, setting motor states through the motor driver, and getting motor power values from your PID controller. It certainly makes your life easier if you encapsulate those three things each in their own class, because it allows you to much more easily duplicate for the left motor and the right motor and stuff like that. So I recommend that you go as far as encapsulating those functionalities in classes, but you don't have to. And if you are going to do so, then the place one would typically put your class definitions is near the top, right after the import statements. Then you might also want to have some functions, some standalone functions. So if you watched my video on classes and objects, I will have explained that classes typically have functions, functionality associated with them. I think the correct term to use is methods for functions associated with classes. And they're sort of built into the class, but you can also create standalone functions or methods. Yeah, I don't know which of those words is more commonly used in Python, but doesn't matter, mean kind of the same thing. I'll call them functions if they're standalone. So that's where you just encapsulate a bit of code in a little wrapper, give it a name, and then you can call that function, probably pass it some information, and have it do its thing and return, often, not always, but often return a number, a value. Yeah, so if you're going to do function definitions, then you typically do that after your class definitions. Then we have a section where we declare all the global variables in our program. So sort of by definition, if you declare a variable outside of any other structure, so outside of a function definition, outside of a class definition, outside of the main while loop of your program, it becomes a global variable, which means it is accessible anywhere in the program. And if you're engineering, big complicated pieces of software, like professional programmers do, then it's generally good to avoid using them, because it's the sort of thing where you can end up, someone else's code can accidentally change the values in your code by modifying the global variables, that sort of thing. But when we're writing relatively small, simple programs, just by one person, or one group, then global variables can be a very useful way to make information accessible in different places in your program. So we're going to use them a lot. And then I've sort of broken it down here because there are kind of different types, or rather different uses for them, right? They are all global variables in that they are all variables and they all have global scope. But some of these will be regular variables in the sense that they are numbers that are going to change over the course of your program. Here we will often initialize them to be equal to 0, just because that's kind of a good starting point. But then as the program goes, we're going to be changing their values over and over again. So they are sort of true variables in the conceptual sense. They're things that are going to vary. But then we're going to use some of them also for parameters. So parameters are things that don't change while the program is running. We choose their values at the beginning, and then they stay fixed as the program runs. So that might be, for example, the PI and D gains for your PID controller. When you're working out the speed from the encoder, you need to know that there are 20 slots on the encoder disk. So somewhere in the program, you're going to have a parameter that says, number of slots is 20, that kind of thing. So these are, so we still use variables to hold these. As far as the programming language is concerned, they're no different to these regular ones, but the way we use them is different in that we put a specific value in them at the beginning, we use that value later, we don't change them. And then finally, it's just worth noting that some of these global variables that we create will not just be numbers or booleans or whatever, but will in fact be objects, i.e. instances of classes, mainly, but I think not necessarily only these classes that we create ourselves. So if I make a class for dealing with my encoders, then at some point around here, I'm going to have to create 2 instances of that class, one for the left encoder, one for the right encoder. And then finally down here, we will have our main infinite while loop. So while true, which means it just keeps looping forever. And that's basically where we put the body of our program, the stuff that needs to keep running for as long as our microcontroller is switched on. And I've been a bit vague here because there's a lot of different ways you can go. But broadly speaking, within that while loop, you're going to need to check inputs, make decisions, and then set outputs, and then keep doing that. Okay. So, right, now I am ready to switch across. Boom. All right. So hopefully you can see that okay. I think the text is big enough. Right, so here is, I'm just sort of showing you how long what I'm going to show you is. Fair amount of it, quite a lot of it's comments. I've tried to keep this as general as possible so that, it doesn't make too many assumptions about what functionality you're trying to implement, so it could maybe be used in the future for someone wanting to implement a completely different robot controller. Okay, so quite a lot of comments. I'm going to talk you through. We've got that whole structure that I just showed you in here. All right, so firstly, just note that there are 2 ways I can do comments in Python. If I just want to comment one line, this is the typical way to do it. I have a hash, and then the text that I want to be the comment. But then you've also got this type here. Typically, this is used if you want to comment out a whole chunk of code. So if I somewhere have, well, I'll just show you here. So if I go 3 little, what are they? Single quotation marks. If I do 3 there, then it says, okay, everything from here down is comment. And then if I put 3 more, then that kind of closes it. And so it comments everything between there and there. But sometimes they are also just used because they look a bit different. So here for the labels for the big sections, I've used that style of comment because it makes the text yellow, just makes it sort of pop out a bit more. So consistent with the flowchart that, sorry, the block diagram that I just showed you, I've labeled the sections. So importing modules, defining classes, defining functions, defining global variables, and then here is the main body with the infinite loop. Okay, so some of these things are easier to deal with than others. So importing modules. For the purposes of this example program, I only needed 2. I'm importing the time module and the math module. You're definitely going to need quite a lot more than that, but that's fine. You'll see which ones are needed in all of the workshop assignments and such. Add any others as necessary. Am I gonna? Yeah, I think I'm probably gonna make this code available for you as well, so you can have a look at it. Scroll around it yourself. Okay, so defining classes. I'm not going to explain how classes and objects work in this video. I have made a separate video about that. I also give a little bit of instruction in the worksheets, but mostly it's that video I made. So here I've just tried to define a generic class definition that follows the standard layout, but is not in any way assuming what you're using it for. So obviously you would use a more sensible name like encoder or whatever, something that says what it's for. But so it's a class. This is the name, just class 1 for now. Then the colon. Then a class always needs to have a constructor method, which is called whenever you create an instance of the class. Again, explained in the other video. So here's my constructor method. Here's the standard syntax for saying this is the constructor method. In this case, I'm just showing you that you can have any number of input arguments. In this case, just for illustrative purposes, I've got 2. So argument 1 and argument 2. And then inside that initializer method, I am taking the values of those 2 input arguments and I'm storing them in instance variables called variable 1 and variable 2. Now, typically, but not necessarily, a class will also have 1 or more methods, almost always really, because otherwise all it is just a collection of variables. So over here, I just have an example of some random method. I have called it first method. Again, you would give it a more logical name when you're making one to actually do something. In this case, it has a single input argument called argument 1, and then the method needs to do something. In this case, we're doing a rather useless thing of increasing the value of variable 1 by 1 and decreasing the value of variable 2 by 1. In case you've not seen it before, note this syntax. Plus equals means the thing on the left is set equal to itself plus 1, and minus equals means the thing on the left is set equal to itself minus 1. Okay, and then if you are going to create more classes, then you would do them in this sort of section. Okay, defining functions. So the first one here is similarly just a agnostic, no particular meaning encoded. Here's what a function looks like. So the syntax is def, the function name, and then a set of brackets with optionally any input arguments you want. So here it's a function called function 1, which takes 2 input arguments called argument 1 and argument 2. Then the colon as usual. And then inside, indented here, you just do whatever the function does. Sometimes functions return data, but not always. Sometimes they just do something. And in this case, we're just doing the minimum possible thing. So we're just returning. So this says this is the data that I'm going to give back. And in this case, it just adds up the 2 arguments and gives that back. So that's the basic syntax. And then I figured if you want to use the servo motor to draw the sort of sinusoidal squiggly line, then you're probably going to need to do something with a function of time. And so I figured I'd just show you how to do a function of time. So part of it is here. So the actual function is here, and then a little bit later we'll see how we sort of get the actual time to pass into this. So it is called some function of time. Because it's a function of time, it needs time as an input. So it has one input argument, which is the elapsed time. And then I need some kind of mathematical probably function. So here I'm just saying that the value of the function f is equal to the sign, which comes from the math module, which is why we have to include it here at the top. And it's why we have to say math.sign, and then the brackets that give the argument. And here we're saying 2 times pi, which also comes from the math module. So 2 times math.pi times the elapsed time argument that we've passed in. And then we return that value f back to wherever we called the function. So we'll see more about how we use that in a second. Okay, if you need any other functions, then you would define them here. Okay, so now we get into the global variables section, which will probably be one of the longer sections in your program. I mean, not as long as the main body, but yeah, basically you're probably going to need quite a lot of global variables of various kinds. So this is just reiterating what I was saying about sort of different uses for them. So some of them will be parameters where we don't mean to change their values during the program. Parameters are generally going to be given some, non-zero value. As we're developing and testing the program, we might need to try different values for our parameters and find the right ones. But as far as Python is concerned, this is just a standard global variable declaration. So its name on the left is assigned equal to the value. Okay, now some of them are going to be variables in the sense that they're things that are going to change as the program runs. So here's 2 examples here. So the first variable is just a single number initialized as 0. And then I figured I would also show you how we initialize a list, which is a set of multiple numbers grouped together. At least one of the worksheets does this, so you'll see it elsewhere. But in this case, I've created a list which is initialized as a set of 5 numbers, where in this case, all 5 of them have a value of 5. Okay, and then some of these variables might in fact be objects, instances of classes. So in this particular program over here, we defined a class called class 1. And so over here, I am creating an object, which is an instance of a class. I'm calling it object1, and I'm saying it is equal to a instance of class 1. This is explained in my other video, but basically we are calling this initialize constructor method. But we're saying I want to create one instance of class 1. I want to pass it 2 parameters because it asks for 2 parameters in the constructor method. There we go. Where am I? Yeah. And so now I have created a variable called object1, which happens to be an instance of the class 1. Okay. Then what we've got here is just some more parameters and variables that I actually need for things that I'm illustrating in this example program. So I have created 2 parameters that are for timing related things. I'm just calling them fast loop delay and slow loop delay. So when you use the time module in Python, all of the times are represented in seconds, and therefore this first one, 0.001, that is equal to 1 millisecond. The second one, 0.1, is 100 milliseconds. And so if I make a loop happen with this delay, then that's a 1 millisecond delay. So I should be getting a 1000 hertz loop rate. That's my fast loop. And then my slow loop with its 0.1, 100 100 milliseconds, that's going to give me 10 hertz. What are these two things for? Okay, so this will be explained in a little bit more detail in, well, a fair amount more detail in the week 6 and week 7 workshop sheets. But basically, there will often be cases where you want to, for example, check sensors quite quickly at a high frequency, and then maybe sort of average those values, or at some slower rate, make decisions based on those sensor values and update your outputs. So it's not particularly unusual to want to check sensors fast, maybe only some sensors, and make decisions slightly slower. So you might want to have things happening at different speeds in your program. Where we specifically need this for the robot is the product engineering group project, is that in order to get our motor speeds from our encoders, we have to check the encoders pretty often at high frequency. Like 1 millisecond is what I end up suggesting in workshop 6. But we don't want to update the PID values that fast. We don't want to check the proximity sensor that fast. And so our main control loop running that at 10 hertz once every 100 milliseconds is sufficient, but we need to be checking the sensors faster than that. And in principle, I could create some other functionality that ran at a different frequency. I could create another timing parameter, set that equal to 0.25, 250 milliseconds, to have something that ran at 4 hertz. Okay, now in the main body here, I'm going to show you two different ways that you can achieve a certain loop frequency. The way that I have chosen to illustrate here for doing the fast loop doesn't require any other variable to keep track of time, whereas the way that I'm going to show you for doing the slower loop does. I'll explain this in more detail in a little bit, but that's why I have to create this variable here, last slow loop time. So this is basically going to keep track of the last time at which I iterated or ran the slow loop. I initialize it at 0 because I don't have anything better to put in there for the moment. We'll see how I use that just now. This one over here, start time, that one I'm using for ultimately for this function of time behavior. I think maybe I actually forgot to call it. No, we'll see. I can always modify it now. Yeah, so, okay, so did I, sorry, excuse me 1 second. Yeah, okay, I did. I was finishing this sample program off this morning, and I actually left something out. Okay, so for this function that I'm going to call later that needs to, return the sine of 2 pi t, I need to give it time, and therefore what I would like to give it is the amount of time that has passed since my program started, or something like that, and therefore, or maybe one state started, and therefore at some point I'm going to need to make a note of the time at which something started. And here I'm setting it equal to the time from the microcontroller's internal stopwatch right now. This time monotonic is explained in more detail in some of the workshops, but basically it is a really handy piece of the time module that references a little internal clock built into the microcontroller. Every time you switch on the microcontroller when it's been powered down, that clock starts at 0, and it just keeps counting in fairly accurate time, but just sort of counting up in seconds from 0. If I stop my program and I restarted without turning off the microcontroller, then this counter does not reset, it just keeps counting up. It only resets to 0 from what I can tell when you actually remove power. But so the net result is that this thing is really handy, but it's only handy for working out that a change in time, an elapsed time. Its actual value is meaningless, but if you check its value now and you check its value in 10 seconds, the value will be greater by 10, and that's very useful. Okay, So we'll come back to some of those. Oh, actually, no. Let me just get this time thing out of the way. So this maybe isn't the most sort of exciting, complicated way to do it, but so over here I've set my start time is just now, and now let's say here inside my infinite loop, I want to get so f of t. Okay, so I'm creating a variable there called f of t, as in f as a function of time, is equal to, and now I need to call my function of time over here, so that's equal to some function of time, and now I need to give it t, right? You know what in a mathematical function would just be t, and I want this to be the time since my program started. And so what I will do here is I'll go time dot monotonic to get the time from that stopwatch right now, minus start time was when things started. And so here I'm just passing it the time since something began, and then it's going to go and put that into this sine function and return the value. So this is something something along these lines is what you're going to need to get the angle that you want to send your servo to for making the pen moving mechanism. Okay, anyway, sorry, I hadn't integrated that into the example very well, so I am just going to comment it out so that if I do share this code with you later, you have it in there. Okay, so now I need to get into the main thing, which is how am I suggesting you implement a finite state machine, and how am I suggesting that you implement timings of things. Okay, so remember from part one, a finite state machine is sort of a conceptual way to represent an algorithm and can also be used to structure your code accordingly. And basically the program, in this case the robot, has some number of states that it can be in. It does a completely different thing in each state. In the previous video I illustrated those as flowcharts. So basically I want to be able to do completely different code behavior depending on which state I'm in, and I want to, under certain circumstances, be able to change from one state to another in a predictable and controlled way. So for my simple approach that I'm suggesting here, the first thing we need is a global variable so that it's remembered always and is accessible everywhere. A global variable that is just going to represent which state I am currently in. It's not going to do anything very clever here, so we have to keep track, but basically we are going to use integers, whole numbers, 0, 1, 2, 3, 4, or whatever, as the names for our different states. I am choosing to make state 0 the state I want to start in. It doesn't strictly have to be the case. I could make this 3 and then, go from there. Okay, so the role of this global variable here is just to always remember which state we are in now. Now, of course, without any further extra programming on our part, that won't do anything. It's just a number. So now we're going to go and look at the main loop and see how we can use this number combined with a conditional in order to implement our states. Okay, so here's the main infinite loop that pretty much every microcontroller program needs, because generally microcontroller programs, you want them to just run forever. And that is, just note that is the entirety of the rest of the program is indented like one tab, which shows you that it's all inside this while loop. Okay, so firstly, I'm going to sort of skim up and down through here a little bit just to show you the structure that I've created for the state machine, and then we're going to go and look into the states to see a few different ways that you could create states, including some stuff that addresses this timing question. Okay, so basically we just have our variable that represents what state we're in, and then inside our infinite loop we have an if, else if, however many else ifs I need, structure that looks at the state variable and does different code depending on what state we're in. So essentially, the contents of each of the cases in this if statement correspond to the flowcharts of the individual states in the previous video. So I say, if my current finite state machine state is 0, then I'm going to do stuff associated with state 0. Otherwise, if it's 1, I'm going to do this stuff. Otherwise, if it's 2, I'm going to do this stuff. Oops. Oh, wait a second. What do I? Okay, hang on. Pausing recording. Why is it not paused? Okay, we're back, and through the magic of pausing a recording and jumping forwards in time, you didn't have to see most of that. Okay, so what I just realized is that I had left in some code in this example that wasn't meant to be there anymore. So look how much smaller it's gotten. And this, of course, will be the version of the code that I actually post. So here's our infinite loop. And as I was saying, we have an if, else if thing. So if state 0, else if state 1, else if state 2, we do different things. Now, I suppose a downside of this relatively simple implementation is that we just have to make sure that we don't do anything too silly. So, so basically, there's nothing built in here that will make sure that this value of current FSM state is only ever set to 0, 1, or 2. So we basically just need to make sure that we never set that to a value that we haven't created a state for. Otherwise, the program will probably crash or just do something unpredictable. But yeah, so let's just not make that mistake. It's easy enough if we only need, a handful of states. Okay, so so inside the main loop, we look at the value, we decide which chunk of code, which flowchart to do, and then one way or another, each of these probably needs to somehow allow for us to change to a different state. Otherwise, we'll get stuck where we are. Okay, so let's have a look at the first one. So this is all explained in the comments. But basically, the way I've chosen to construct state 0 here is as an example of a state that kind of holds priority until some condition is satisfied. So use this approach carefully because nothing else can happen. The main loop won't keep looping. We're just going to stay in this piece of code until a certain condition happens. But this is perfect, for example, for the idle state for your robot when you first switch it on, waiting for the user to press the button. So in order to get that sort of functionality, inside our state, we need a while loop that will keep looping for as long as some criterion is true, for as long as continue condition is true. In practice, we would need, so then inside the while loop, we need to do something, and we kind of need to make sure that that something involves checking maybe a sensor, most likely option, and updating the value of this variable. Because if we never let this variable change inside this while loop, then we're just trapped in this while loop forever. We're never going to get out of it. But if, for example, I am inside this loop checking the value of a button, and when a certain something happens with the button, then I change this continue condition from true to false, then we'll be able to get out of this while loop, proceed onwards to the rest of the code. And then the way that I've chosen to structure this one is that, so we loop around this while loop for some amount of time, and eventually when we break out of it, we come to here, and we change the state to something else. I've chosen 1 in this case. Now, just for completeness, so what exactly is going to happen here? So we run this line of code, we change the value of current FSM state to 1. What code is going to get run next? You might think it would immediately go in here, but it won't, because remember, this is part of the same if statement that we started here. And the way if statements work is once you've done one of their options, it just skips to the end and doesn't do any of the others. So in fact, what happens is after doing this line of code, we go through the rest of the cases and we pop out here, which is essentially where this if statement ends. We see what is the next line of code. Okay, so it's a time.sleep, which means we're just going to put the microcontroller into hibernation for a moment. The value of fast loop delay is 1 millisecond, so it's just going to chill here for 1 millisecond. And then there's no more lines of code, so what's it going to do? It's going to, the while loop is going to bring us back to the beginning, and we're going to come here, and now we've changed the value of FSM state to 1. So is it equal to 0? No, it's not. Is it equal to 1? Yes, it is. Okay, so now we're going to do this state. So here I've chosen to show you an example of a state that allows the main while loop to keep iterating while this state is active, and kind of relies on this main while loop to keep redoing what's in this state for as long as we're in that state. And also the way that I've structured it here, the timing, the frequency at which the actions of this state get done for as long as we stay in the state depends on this time.sleep at the end, which is kind of optional. You could, I think in many, from what I can tell, if you just didn't have this, then the loop would go around significantly faster. It would basically just go as fast as the processor speed combined with the complexity of the actions in here allows. And sometimes that might be what you want. I did a bit of research. There's not much by way of downsides for doing that, except maybe it uses a bit more power, electrical power, from your batteries sometimes. And it also means that you don't know what rate this is going to happen at. So I don't think it really matters that much, but I decided to show it this way because in the workshop manuals, I show you this way. I think it's one of those choices that you just have to make a choice and it doesn't really matter all that much. Anyway, so when current FSM state is equal to 1, we come in here, we do some to be decided actions associated with the state, and then we need to allow for the possibility of changing to a different state. So I've again done it in a fairly general way here. So if some condition is true, we will change the state to 0. Otherwise, if some other condition is true, we'll change the state to 2. And if neither of those things are true, then we won't do this, which means we'll come to the end of this case, which means we'll jump to the end of the entire if statement. We will sleep for 1 millisecond, then we'll come back because of the while loop. We still have FSM state equal to 1, which means we say no, yes. We come back here, we do this code again, we check our conditions again. Let's say we're still not changing. We come down here, we wait a millisecond, we go back to the beginning. We're still 1, we go in here, and now let's imagine that something's changed such that state 2 condition is true. So I do the things for the last time. I come here, I say state 0 condition false, no, state 2 condition true. Okay, change the state to 2. Then again, we come down to the bottom, we sleep for a millisecond, the while loop brings us back to the beginning, and now we go, no, it's not 0, no, it's not 1, yes, it is 2. So the state 1 there is an example of something that allows the main loop to keep iterating, doesn't block other processes that you might want to be doing within that iteration, and where the timing is determined basically just by how fast we can go around the infinite while loop. And in this particular case, I've chosen to slightly limit the speed we can do that by having a time.sleep for 1 millisecond at the end. You may or may not want to have that depending on what you're doing. Okay. Now let's go and have a look at how I've structured the last state here. Excuse me. So this one is an example of a state that allows the main while loop to iterate again, but also where we use the stopwatch functionality of time.monotonic to ensure that we're doing the contents of this state at a consistent rate determined by a parameter. In this case, I'm using slow loop delay. Is this too detailed? No, I don't know. Well, I'll come back to that. So I was wondering what to say about this point here. The precision with which this structure will keep our timing to what's specified by slow loop delay kind of depends on the fast loop delay, because every time we come around, we're sleeping for 1 millisecond, and while we're sleeping for that millisecond, nothing else can happen. And so by having that, we kind of give our timing resolution of the whole thing, we make it 1 millisecond. If that's confusing, just ignore me. Sorry. Okay, so let's have a little look at how this one works. So incidentally, this is what you're going to want to use for your main control loop of the robot, where you are calculating motor values based on the PID loop, checking your proximity sensor, those sorts of things. So comment, blah, blah, blah. In order to implement this timing functionality, the first thing we need to do is get the current time right now. So I say time now is equal to the value returned from the time.monotonic stopwatch that I described earlier. Now here's the bit that essentially achieves our timing. So what we want to do is see whether enough time has elapsed that we want to run our code again. So here we say if the time now that we just got minus the last time that we did the stuff, sorry. Yeah, okay, ignore that. So the time now minus the last time that we did this stuff, so that's the elapsed time since we last did the contents of this state. We're asking, is that greater than or equal to the loop delay that we want? So remember, in this case, slow loop delay is 0.1 seconds, 100 milliseconds. So let's imagine that we've just done this. So time now is only, 1 millisecond more than the last time we did this. That means this if comes back as false, which means we don't do any of this code. We just go to the end, we sleep for a millisecond, we go back to the beginning, nothing's changed, so we come into this state again. Now 2 milliseconds have passed, so we still don't do this stuff. Zoop, 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 zoop. So we whiz around like that until eventually enough time has passed. So let's say now it's been 101 milliseconds since we last ran this code. So we get the time now. We say time now minus the last time we did this. So let's say now it's 100.5 milliseconds. Okay, so that's greater than the 100 milliseconds delay, which means this if statement is true, which means we now do the stuff in here. So the first thing we absolutely have to do is update the value of last slow loop time to the current time. So we're doing the contents of the state of the loop now, which means we need to note the fact that this is the last time that we did. So we update this value, then we go and do whatever functionality we actually want to do associated with the state, and that kind of needs to include the possibility of changing to a different state. In this case, we just got some arbitrary state condition 3. If that's true, we're going to go back to state 0. And then we will pop out here, sleep for another millisecond, loop back around with the while, and if we're still in state 2, we'll come back down here, and now we get the new time. We compare it to our updated last slow loop time that we've just written down the time for, and so nowhere near this much time has passed, so we go around doing nothing until that much time has passed. So yeah, so this approach here is good for doing something at a fixed predictable rate. It will stick, it'll do a very good job of keeping that time subject to 2 constraints. Firstly, if the stuff in here takes longer than this amount of time, then it all stops working, right? Because this code takes as long as it takes. This construction can't make the processor any faster. So you just have to make sure that everything you're trying to do in this loop happens within the available time. If you're ever wondering whether that is the case, you can do useful things like print the value of time now, print the value of time dot monotonic before and after you do stuff, and you can use that to see exactly how long that stuff takes to do. But generally, these processes are very fast, so any sort of just normal lines of code that you put in here would almost certainly comfortably happen within 100 milliseconds. Where you need to be careful is if you're like interfacing with external components, like if you interface with the time of flight proximity sensor the wrong way, then it can take up to 40 milliseconds for it to give you an answer, during which nothing else is happening. So that sort of thing could potentially start interfering with your ability to keep to the designated timing. Just keep an eye on it. Output, time values, print stuff to the terminal if in doubt. But yeah, so that's the first caveat. The code that you're doing needs to fit within the designated time. And the other thing is that if you do have a short sleep outside of the if structure, just at the end of the main loop, then just keep in mind that that affects your sort of precision, because while we're sleeping over here, we're not checking whether enough time has passed. Now, for the values I've chosen here, where this one is 1 millisecond and this one is 100 milliseconds, that doesn't really matter, because a precision of 1 millisecond on a time of 100 milliseconds is pretty irrelevant. But if I had for some reason made this 10 milliseconds, then suddenly I'm doing my 100 milliseconds to 10 milliseconds precision, which means I might end up doing it after 106 or something rather than exactly 100. I could also make this one smaller. I could make it like 0.1 millisecond if I wanted higher precision, but still wanted to include this to give the processor a little pause. Yeah, so just be aware of those things. Okay, now I'm going to be honest. I realized that this was a bit long and a bit rambling and not my best ever video. I hope it was still helpful. My excuse is that I'm a little bit sick, and I also have a lot to do, so I didn't have enough time to like carefully script this. Still, I hope between this and the previous one showing you the algorithms, I hope that it is helpful. And then, of course, remember, there's also all of the little separate ones that I've posted, we'll be posting today, explaining little specific aspects of Python. Yeah, I will post this code as well on Brightspace today. And yeah, okay, that is all I've got for you right now. Thanks for your attention. Hope I explained this stuff all right. And yeah, come to the Wednesday Q&A sessions if there are things that you would like to clarify. Okay, bye for now.